We had a last-minute unforeseen circumstances that our next speaker could not make it in person. So as a result, we are going to have Dr. Gitta Kutyniok on Zoom for the first lecture of today. But because when the speaker is in the room, it's a lot easier to see the audience and ask questions and ask for somebody to ask a question and so on. We think it might be quite efficient because the speaker cannot see you as she talks. Feel free to put the questions in a Slack, and we could relay to a speaker every now and then, and so on. And then, of course, there's going to be dedicated Q&A time, where with the help of our AV team, the speaker will see the people who ask questions and so on as well. So we try to make up for the in-person interaction through some tech, but also through the Slack channel and so on. So hopefully that could all work out. So it is my pleasure to introduce Dr. Gitta Kutyniok, who is currently the Bavarian AI Chair of Mathematical Foundations of AI at Ludwig Maximilians University in Munich. She also held visiting positions at prestigious US institutions, including Princeton, Stanford, Yale, Georgia Tech, and Washington University at St. Louis. After beginning a full professor of mathematics in 2008, she moved to Berlin and held an Einstein Chair of Technical University of Berlin until 2020. Her research focuses on applied and computational harmonic analysis, AI, compressed sensing, deep learning, imaging sciences, inverse problems, and their applications in diverse fields such as life sciences, robotics, and telecommunications. So please join me in welcoming Gitta to the stage.
Thank you very much for the very nice introduction. I also apologize for not being able to be here. So I hope that still, the communication goes as, was just mentioned. I would like to tell you a little bit about reliable AI in medical imaging, a bit from a, let's say, also theoretical viewpoint, but don't worry, it's not too deep theoretically, so I put everything on a very high level to show you a bit more of the concepts and also the questions people are wondering about. And as I say here, successes, challenges, and also maybe limitations in that sense, where in the future we actually need to rethink some aspects and maybe go beyond what I will tell you. Now, I think we all know the current impact of AI, on our society. What we expect is during the next years, a radical change of society in basically every aspect. So you see some things already at present, autonomous driving, robotics, telecommunication, sensitive areas like, for instance, the legal system, also the job sector, and then the whole area of sciences, and certainly first, medicine, and health in general. That's why we are also here, but also biology, astronomy, digital humanities, and so on. And everything got a huge push, also concerning the public attention lately, because I think we all know of large language models and ChatGPT, which put things in a certain sense even on a maybe even higher level. And what we also observe now, if we get closer to science, is that we observe a change of paradigm. So I myself experienced this very strongly because I come from the area of imaging sciences. And since 2012, these new methods, model-based, machine learning-based methods really changed the area significantly. We could observe a change of paradigm, and within a very short amount of time, these new methods reached the state of the art, denoising, edge detection, in painting, and so on and so on. And so in this talk, I would like to discuss questions also with you, which I think are absolutely crucial for these areas. So for instance, typically one, and this gives the best result, does not use AI or, for instance, deep learning end-to-end, but to combine it with physical knowledge. So this is a big question because we know the physics, for instance, of the CT scanner. So why throw everything overboard, which we actually know? Why let the artificial intelligence relearn everything? And so the question is how to best combine those. So this will be one topic of my lecture. Another will be also then in the end, we need to also explain the results, because Well, I mean, we can certainly trust the AI, but as we all know, it is still unreliable, and we also see examples of that. So what one typically should do is also check a bit. I mean, whether there's a reasonable outcome and how the results were achieved, but also this helps us a bit understanding in general, I mean, how the AI comes to the output it generates. And another, let's say, also guideline of this talk and of this lecture will be, are the results reliable? Now, can we trust them? How can we improve maybe trustworthiness? Because on the other side, I mean, there are also a lot of indications and discussions how trustworthy and reliable things are. So there was an interesting incident, maybe you were aware of this 4 years ago at one of the big AI conference. One of the researchers, Ali Arpimi, he won an award. And in his plenary speech, he claimed that machine learning is still at the level of alchemy. As he said, researchers do not know why some algorithms work and others don't, nor do they have rigorous criteria for choosing one AI architecture over another. And that raised a big discussion to which extent, I mean, this is okay that it's alchemy, that it's a lot of trial and error, or to which extent we actually need also a more deep understanding, and in that sense also a more deep theoretical understanding. And also this will be something which we discuss. Everybody can have different opinions, but here in this lecture, I would show you a little bit, let's say, the viewpoint from a more theoretical perspective. And yeah, so in this regime, since we are, or you are in the UK, maybe I should also mention Stephen Hawking, who said the development of full artificial intelligence could spell the end of the human race. I think we are very far from this at this point, but still I think reliability and trustworthiness is a major issue. And that also has a reason, because there are still a lot of problems. For instance, problem with safety. There were accidents already involving robots. So an autonomous car, self-driving car is also a robot. There were several problems with security. One can hack, for instance, in a hospital IT system, change things slightly so that the artificial intelligence doesn't recognize it, but then reaches strong decisions. All of these methods are very data hungry. So privacy is a major concern, and such violations happen on a daily basis. And then also problems with what I might call responsibility. As said, I mean, these decisions, I mean, these algorithms are typically black box decisions. So the question is, can we look into those? Can we understand how they work? And also, often decisions are biased depending on the training data, because in particular in the health sector, I mean, getting large data sets is a huge problem. And so this is one also major concern for reliability. And in that sense, I think it's fair to say that one current major problem worldwide is the lack of reliability of AI technology. And there are also now, as you see worldwide in politics, major directions to cope with this. So, I mean, for instance, there was just the AI Act of the European Union, which poses restrictions on reliability. And then even the G7 in Japan at their last meeting started the Hiroshima AI process to also regulate and AI in a much more sophisticated manner, making it reliable. And so, I mean, from my perspective, I mean, what it takes also to get true reliability is a deep understanding. So we need to understand it in its depth, and that can only be achieved by a theoretical understanding. And that way you can get then within model situations absolute security and absolute safety. And then the question is how to translate it also to the real world. And I would like to show you, let's say, a little bit from this world. So let me start very basic so that we are all on the same level. AI and, I mean, also deep neural networks are nothing new. They started in 1943 with McCulloch and Pitts, and they wanted to introduce AI, artificial intelligence. And their idea was, since we humans believe we are intelligent, what they wanted to do is they wanted to mimic the human brain. Now, the human brain consists of neurons which are interconnected. And so the idea was to mimic this, to develop a mathematical model for this, and then use this for learning. Now, so the first task was to develop artificial neurons and then connect them to an artificial neural network. Yeah, so in that sense, I mean, this led then, and we'll go in more details now, to deep neural networks, which are, I think today, everybody agrees, one of the main workhorses for artificial intelligence. So an artificial neuron, what is the mathematical formula for this? Well, I mean, this is a neuron. So the way it works is we have here signals coming in, x1, x2, x3, and so on. They might be amplified by passing through these dendrites. And this amplification is modeled by these weights. So what arrives here is x1 times w1 plus x2 times w2, and so on. Then here in the soma, everything is collected. So here we get the sum over xi wi, so x1 plus w1 plus x2 plus w2, and so on. And then the neuron has to decide whether to fire or not. And this is modeled by a bias term. So this sum, as you see here, is now compared to this bias term, and depending on whether it's larger or less or equal, the neuron fires or not. So this is extremely simplistic, and we all believe that this will not work very well. And this is also not exactly what is done. So in fact, here, this function, this so-called activation function, is a bit more sophisticated. It is now typically what's called the ReLU, the rectifiable linear unit, which is, so if the sum minus b is negative, then a 0 is outputted, but in the positive regime, the exact value is output. So now these are artificial neurons. We will see it a bit more, let's say, detailed on the next slide, and then we connect them to get an artificial neural network. And what we then train are these weights and these bias terms. Okay, so a bit more mathematical. This is now an artificial neuron. It is a function which maps x1 to x2, x3, and so on to this term. We saw the sum and the b, the bias term, already before, and now we have here this activation function. This activation function can have different values. I said before, typically it's now the rectifiable linear unit. It can be the heavy side function. This is what we saw before. So there, this f only had outputs 1 or 0. Okay, so this is an artificial neuron. It's a purely mathematical object. So now we connect them to get an artificial neural network. And let me just make this one example so that it's a bit more, let's say, precise, not precise, but a bit more, sorry, how do I make this small? Okay. Yeah, I don't know, I made it accidentally larger. Okay. So now, so this is a neural network. All these yellow dots are now artificial neurons. They get their input from here, and then there's an output. This gets the input from here, output, input from here, output, and so on. So now we can phrase this in a formula. So how do we do that? Well, we have here, we start here, we have here x1, x2, x3. This is this x here. The next is we encode now these connections in a matrix. And so see, the first output is this x1 times this weight plus x2 times this weight. This is now this line here. Then the second is x3 times this weight. This is this line, and then I have this line. So this encodes these connections. This is this matrix W1. Then I add the bias terms, and I also apply this activation function all in the neurons. So this is B1, and this is his activation function, which is now applied to each component. So this is exactly this part up to here. And now I have, again, the next connections. This is now this matrix W2. So now I go from R3 to R2. So this is encoded here. Again, I add bias terms, then an activation function. So you see how things are built up. So we always have these weight matrices, these bias vectors. This is what we train later on. And then we have the activation function. And so therefore, a neural network, then in its full glory, feed-forward neural network looks like this. It is a formula of this type. And again, you have here these activation functions, and the TLs are all these affine linear functions, Wx plus b. Okay, so the main message here, I mean, it's not important to understand all details. The main message is here, the neural network is a mathematical object, so you can access it with any, let's say, theoretical tool you can imagine. Okay. Yeah, so I mean, if there are any questions, you can also, I guess, through someone ask me questions in between. So I hope that there is no then delay in understanding because of that. Okay, so this is a neural network. Now let's look at a bit more sophisticated one. This is also what you might have seen maybe also in the other talks. So in imaging sciences, we typically take not the, let's say, custom feed-forward neural networks, but convolutional neural networks. So they, so here, if you go back, I mean, one layer basically consists of these FR linear terms, and then you have the activation function. So these convolutional neural networks, these functions are convolutions, and there's another part of the layer. So the way that works is, so convolutions are very good. So choosing the weights as convolutions, because for instance, for classification, it doesn't really matter whether the object of the image is on the left lower corner or the right at upper corner. No? And so therefore, I mean, convolutions don't really care about that. There are very efficient weight matrices in that sense. They treat all aspects of the image the same. And so what is chosen then often are these convolutional neural networks. The activation function is again, I mean, component-wise, typically again, the ReLU. So this is similar to before. And then, I mean, since this convolution, the fact that we use convolutions blows up, usually the dimension, in each layer, there's another operation, which is pooling operation, which basically brings down again the size. And there are several directions one can take. I mean, max pooling, min pooling, average pooling, depending on the application. And so basically then it looks a bit like this. One has the image here, one has here the convolution and activation, so ReLU. Then the next step is the pooling layer. So this shrinks the size, and then again, convolution, activation, pooling, and so on. So it's a bit more, let's say, sophisticated than the classical feed-forward neural network. Okay, so now, I mean, I would like to briefly discuss what the key theoretical directions are, and then we will delve into imaging sciences. And for that, I would like to show you just on a very high level how a neural network is applied. And this will also lead us in a canonical way to the questions we need to ask, also for ensuring reliability. So what do you do with a neural network? Well, I mean, you classify, for instance, sets. Or you can say it a bit more complicated. You have a very complicated function in the background, which does the classification, but you don't know the function. What you have are just images and their labels. But what you want to know and learn is this very complicated function, which for any image gives you the correct label. Okay, and so here, for instance, I mean, you have your images, people like images of cats and dogs. So for instance, you would like to map all the images of dogs to the value 1 and of cats to the value 2. And typically these images lie on a very complicated structure, because if you have, let's say, an image, you cannot just choose any random collections of pixels. You will not see a natural image. These natural looking images are in this high dimensional space very complicated. So anyhow, let's assume there exists this function, which gives for every natural image the correct label. Okay, so I have these samples. I split it into the training and a test data set. And now the first thing appears, I have to decide which neural network to take, because what I want to do now is I would like to approximate F by a neural network. Because, as we saw before, if we go back, a neural network is just a function. It maps something from some space, an image, for instance, to some other space. Okay, so this complicated classification function, I would like to now approximate or learn by a neural network. So first I have to decide which neural network actually to take. This is already quite difficult, and coming back to what I said before, this plenary talk, alchemy. So this is a lot of trial and error. I mean, everybody who has already trained a neural network knows. I mean, it's not really clear which network to take, how many neurons in each layer, how many layers, and so on. So this is the first. We need to select the architecture. Then we need to train it, and training means learning the weight matrices and the bias terms. So here we have, and so this looks now a bit complicated, but remember, these were these weight matrices and the bias terms. This is what I need to learn. And what I aim to do is I have here my neural network function. So in my neural network, I input my images, and I would like that I get the correct labels. And here, this is a so-called loss function. For instance, it's the square loss. So I take the difference between these two outputs squared. And this I want to make smaller. And so I sum then over all my training samples. And M is usually in the millions. And there are classical algorithms to solve such an optimization problem. For instance, gradient descent, which basically starts somewhere in the energy landscape and then aims to find a minimum. But since M is in the millions, gradient descent cannot be directly used because you cannot compute a million gradients each time. And so therefore the stochastic gradient descent came up. So you basically just choose the gradients of some of these samples randomly and then hoping to get a good average. And this is already a mystery why this works that well, because the landscape over which you optimize and where you find now these minima is very complicated because this, what you optimize over, is highly non-convex. Anyhow, so once you've done that, well, I mean, you get your matrices, your weight matrices and your bias terms, and then you hope that now, if you now look at the test data set, so at some images with labels which the network has not seen before, that things work out. Meaning, if you have a trained neural network, you input those, that you get the correct output. Yeah, so this is in some sense the generalization to unseen data. Okay, so that's the canonical workflow. I'm sure most of you know that. So what questions do we ask? I mean, the first asked questions, as you saw on the previous slide, is which architecture to choose. And so this is a question which you can study, for instance. I mean, this is nothing we will go into details, but let me just say this is maybe the most explored theoretical direction. It aims to study how many layers the network needs to have, how many neurons in each layer to get, let's say, the approximation capacity we need. Because as you see here, we have here certain functions, and we need that the network which we train gets close to those. Yeah, and so this is what this area of expressivity studies. So it's basically purely approximation theoretic. Then learning. Why does the learning algorithm work that well? Yeah, so the problem is non-convex. I still get a good result, a good neural network, which then also generalizes to unseen data. And this is still a big mystery. A lot of research is going in this direction. So optimization, optimal control are used. And also quite exotic areas lately, like, for instance, algebraic differential geometry, which indeed, I mean, aim to study the shape of the local minima, in a sense, the geometry of those. And then maybe what is typically called the holy grail of the theory is generalization. So can we get success guarantees on the test data set? Can we say beforehand how good the network will do on unseen data, and that way also study robustness problems, for instance? So this is usually a very probabilistic statistical question. And let me just, I mean, this will not be let me just spend one slide to show you a bit about this generalization direction, so that you're just familiar with what happens there. So one key question is also, as you might know, if you ask practitioners which neural network to take, well, they say, take the largest, which still fits in your GPU. Yeah, so for some reason, large neural networks are extremely effective. And this is also still something which is not understood at all. There are some results, but I mean, we need to understand this before we need to talk about what is a generalization. And so there's a very, very famous picture. It's so-called a double descent curve. And so let me walk you through that so that you see what people now aim to do in this regime. So let's first take a look at the left-hand side. So this language which you see there comes from statistics. So let me translate it. So this is the size of the neural network, the capacity of the hypothesis class, the size of the neural network. This is the error. And certainly the training error, as the network grows, goes down to 0. Because the network is larger, you have more free parameters. And so the training error, I mean, it fits the training data better and better. So that's very natural. The test error, after some point, goes up again. And that's what's called overfitting. Because then the network has too many free parameters and is aiming to enclose the training data too well. And then it is a problem if you have new points, they might be easily misclassified. So this is this curve. Okay, so this is very well theoretically understood from a statistical viewpoint. But this is not what happens these days. What happens these days is what you see here. And you see now the left-hand side coincides with what you see here. But you have here now a right-hand side. And what you see is as the network size grows further, the test error again goes down. And so this is what this means, taking the largest network which fits in your GPU. The larger, the better. So therefore, I mean, you need also these huge data centers to train, I mean, really effective neural network, which is, I mean, in a certain sense, also a huge problem in various respects. I mean, also from an energy viewpoint and so on. But what people aim now to do is to understand, for instance, this curve. There are a lot of common approaches, which I don't want to discuss in details, but there's a lot of research going on to understand this, and then also ideally get error bounds on the generalization error. So understand here this test error, model this very precisely. Okay, so that's the generalization. Now, this are all questions you need to ask during the training process. But if you have now a neural network, you bought your software and you get your, let's say, AI encoded in there, you don't have any chance to understand what the training data was, how it was trained. What you then need to do is you need to be at least able to explain the results. And this also has a legal viewpoint, because I talked about the EU AI Act, and for instance, the right to explain, a right to explanation is then also a legal requirement, which algorithms need to fulfill. So explainability is a key direction. This aims to understand how networks reach a decision. And maybe another direction, which is to my mind very much neglected, but I think as absolutely crucial, is also the question whether there are fundamental limitations. Because, I mean, there might be limitations. I mean, neural networks and AI is not a Swiss Army knife. So talking about that openly and seeing how to overcome that is something I think we need to do. And so in the very last part of my talk, I will talk a little bit about this area of explainability, because I think it's also very important in the health sector, and then also fundamental limitation, again, because in the health sector, we need to rely on the results. And if there are fundamental limitations, one needs to be aware of that. Okay, so let's now delve a bit more into imaging sciences. Again, a bit from a, let's say, theoretical viewpoint, but again, not too deep. So everything, as I said here, is what we call an inverse problem. And in medical imaging, most of those problems are of that type. Now, because what do you typically have? You have your data, for instance, the interior of a human body. Now, you take measurements, however you do that by a CT scanner, MRI, and so on, and then you would like to get your data back. Basically, you would like to invert this process. And ideally, you would like to get the exact same data which you inputted back. So therefore, it's an inverse problem. This is the forward problem. You take the measurements, but then you want to invert this process. So therefore, it's an inverse problem. And typically, it's written in this way. So you have here this map K, or if you would kind of like to call it fancy, an operator K, which takes the input F, maps it to the measurements G, and then you would like to invert it. So for instance, also in imaging sciences, typical question is you have an image, but you're missing certain parts. So the K took out certain parts and you would like to invert it. So these inverse problems can be very hard. And let me just explain to you what it means by they can be very hard. So the typical setting, this is what I said. We have our map operator, which maps from some space of natural images to the space of measurements. And then we would like to solve this in the finite dimension setting inverse linear system of equations. And so there's a notion for what it means that this is hard. And so this is what is called an ill-posed problem. Yeah, well-posed means everything is nice. So what would it mean that things are nice? Well, first of all, you would like to have that there exists a solution. So you would like to know that there exists some data which actually can be, for which y are the measurements. If that data doesn't exist, you have a problem. Second, you would like that data is unique. If you have a lot of choices and let's say there are 1,000 humans for which the measurements are all the same, you have a huge problem. And then last but not least, you would like to have stability. So, I mean, if, for instance, your measurements converge, then, I mean, or are modified, I mean, then let's say, again, in medical terms, the human which was put in the MRI scanner, let's say, should also not differ too much. But unfortunately, most of those problems are ill-posed, and for most, the uniqueness condition does not hold. So you have multiple data which has all the same measurements. So let me show you some examples of ill-posed inverse problems. As I said, I mean, one is this problem which is called in-painting, so you have missing data. This, for instance, also occurs in limited angle computed tomography. So here the K just takes out certain parts and then you would like to invert it. So basically you would like to, again, fill in this missing data in detail. So this is one problem. And why is this ill-posed? Well, I mean, here I can fill these black parts in however I want. Yeah, I mean, I don't know, I can leave them all black. I can fill them in a different color. So in that sense, I mean, it's highly non-unique. Magnetic resonance imaging is another problem. So here, what do? The scanner works as follows. You take here, I mean, you have samples in K-space, so Fourier samples. And depending on how you take your samples, so here, for instance, yeah, so this, what you see here, this black and white background is the Fourier transform of this image. Yeah, so this is how the measurements are taken. You take images, pixels are, pixels in K-space or Fourier transform, and then from the values at these red dots, you aim to reconstruct this image. But I mean, typically, I mean, one aims for very few samples so that the patient doesn't need to lie too long in the scanner. And if you do that, you get a blurry reconstruction and also maybe your uniqueness. You have other problems if you take other types of measurements. And this is something which, if you have heard of this area of compressed sensing, which is advocated there a lot, taking, let's say, random measurements, taking more in the interior, so close to the low frequency part and less the exterior. So that way you can really bring the sampling rate down. But this has nothing to do with machine learning. This is, in a sense, I mean, a method which was developed basically 10 years ago. But in any case, this is also an ill-posed problem. In particular, also uniqueness is a key issue. Another problem of this type is also feature extraction. So you have, for instance, here, these are images of dendrites, and you would like to maybe separate the dendrites from the spines for further analysis, for instance, for Alzheimer. So the operator before the map K takes these images and adds them, and now you would like to invert it. So you would like to, again, separate those images. Again, an inverse problem. So all of those, basically all of those problems, I guess you know, in a sense, I mean, certainly not classification, but typically imaging problems are of this inverse problem type. Okay, so how do you classically solve this? And so here also another image maybe, so to show you the difficulties. So typically you have nice data, you take measurements which are a bit messy, and then from these you would like to recover your data which you put in. So there's a very classical method to solve this problem, to recover f from k and g, which is built on what's called Tikhonov regularization. This is a bit more sophisticated version, which is what's called sparse regularization. So let me walk you through that. So what we solve is an optimization problem. Again, as we saw before, we look for an optimal f. This is my input data, which I'm looking now for. And what you see here is if you bring this term down to 0, if you can do that, this ensures that you solve this problem as accurately as possible. So that's the so-called data fidelity term. You aim to match your measurements as good as possible. Now we saw, since we have these ill-post inverse problems, that we can have multiple solutions. So this creates an uncertainty, and it's not clear how to cope with that, and therefore what is then added are regularization terms. So the regularization terms, through those one can incorporate properties of the original image which one aims to have, and there's a whole zoo of those terms. So bringing this down to 0 is good, but then bringing this to 0 helps to recover the correct image. And sparse regularization is one philosophy. You see this here. So what it basically aims, we will see it a bit more in detail on the next slides. I would like to walk you through that, because we will then augment these traditional solvers with machine learning and with AI. But first we need to I just need to recap a bit of what has been done before. Now, what you see here is you have your f, you have here a sequence, and we see examples of those in a moment. The philosophy here is that for every type of images, there's a representation system which gives me a very efficient representation. And if I then optimize for this efficiency, I can get a very natural looking image. And so optimizing for efficiency is usually the L1 norm, because the L1 norm promotes sparsity. So and again, we will see this a bit more on the next slide, but let me here already show you a little bit the intuition behind. So what you see here is, let's say, possible solutions are all on this line. So whatever you are solving. But now what you want to get are solutions which have very few large terms. Because these are efficient solutions. Typically, you would like to have a vector which has just very few non-zero entries and all other zeros. And on this line, there are actually 2 of those. This is this point and this point. So now if you optimize the L2 norm here, this L2 ball, what would you do? You would take the L2 ball, you would blow it up. You hit the line somewhere. You will hit it here, and this is your solution, your minimal L2 norm. And that's not great. But if you take the L1 norm, where the L1 ball is like a diamond shape, you hit the line here, which is exactly what you want. So therefore, the L1 norm is that often used in all these problems which have to deal with sparsity in a certain sense. So that's called sparse regularization. Okay, so let's fill this a little bit with life. Let me just say first, for data processing, overall sparsity is...
Excuse me. Can I ask a question from Slack?
Oh, yeah, sure.
Sure. So Giovanni is asking, can you give an example of an unstable inverse problem?
Oh, unstable inverse problem. So yeah, yeah. So magnetic resonance imaging is also unstable in that sense. So the question, I guess, was this problem? It depends. So this condition is a bit sophisticated because it also deals a bit with which norms you take. So here you're in the infinite dimension setting, and so therefore the norm plays a role. If you're in the finite dimension setting, all norms are equivalent. So in that sense, here it's a question in which norm you view your problem. And so for magnetic resonance imaging, you can take norms where this problem becomes unstable. Okay, yeah, so please feel free to ask questions because I don't see you, so therefore it's important, I think, to stop me when it's also too fast. Okay, so for data processing, I think sparsity is one main paradigm change we have seen over the last years. And so sparsity, what does it mean? Just here in a nutshell, if you have, let's say, a vector, it is k sparse if it has k non-zero entries. And so usually, I mean, the mathematical model are just planes in a certain sense. So these would be the two sparse vectors in R3. And often, since you don't have zeros typically in natural imaging, as you might imagine, there's a relaxed version which are called compressible signals. So these compressible signals means the others are not all zero, but they are very small. So if you sort, if you have your vector, you sort your coefficients, then you get a power law decay. Yeah? So this red line would be a sparse vector. So you have some which are positive and the others are zero. But here, these compressible signals, they have large entries, but then the others are just very small. Yeah? But this is what is typically imagined, that in fact, the world is compressible. So for any type of data, you will find representation systems, which gives you a very efficient representation. So this over the last, I don't know, 10, 15 years, there's been a ton of research in this direction. Also algorithms, dictionary learning algorithms, which do that automatically. So here, this is maybe the most famous one, the wavelet transform. So here you see an image. This is the so-called wavelet transformed image. Also JPEG 2000 is based on that. But if you like, you see here the wavelet system. So what you compute here are inner products of your F, your image, with here wavelets, for instance, these functions. You get an image of this type. And what does it mean? Well, it means only the white dots are important. All the black dots are zero. You can neglect them. That gives you these compression rates. And then from these white dots, you can reconstruct your original image with high accuracy. But I mean, so this sequence, which we also saw during sparse regularization, is a sequence which is very sparse. And here you see some of these wavelets. So basically, you write your image in terms of these wavelet elements, like a building block system. And there's a bit more sophisticated system than wavelets, which is based on the fact that in imaging, directional structures are important. And so also because of the human visual system, because we are trained to recognize edges, and also our visual system is designed that way, that we recognize edges very clearly. And there's a system which is adapted to that. So they look a little bit more directional shaped. They are called shearlets. They appear in any direction. They appear at any scale, at any position. And let me just say, you can do something similar then for wavelets. So here you can, in fact, even prove theoretically optimal compression rates for a certain model class of functions. And also, if you like, I mean, there's an extensive software library now also in TensorFlow where you can download code and test this out. Okay, so this is, I mean, let's say the classical viewpoint. So we have our solver, we maybe do sparse regularization, we use, for instance, shearlets for it, and then we solve our inverse problem. Now, let me show you one example where this doesn't work anymore. And so this is computed tomography with limited data. So I assume most of you are familiar with this. So what does it do? Well, it computes the radon transform. I'll give you a little bit more details on the next slide, but let me now stay on the very high level. So what does it do? You have here the interior of the human body. You compute line integrals through it. And so for each line, you basically, in a sense, accumulate the points and then plot this here. So therefore, you get this one-dimensional curve, and this is one slice of the sinogram. And then the device is rotated. So you acquire the data at every angle, and that gives you this sinogram. So you have your 180 angles. And from the measurements, you would like to reconstruct a very classical inverse problem. This becomes very difficult if you have limited data. Now, limited data is always a huge problem, as we know. There are two different problem settings. One encounters here. One is low dose CT, which means maybe I acquire the data only at every third angle. And usually this is done to not expose the patient to too much radiation. Another one is limited angle. And limited angle is, for instance, in electron tomography, because there you cannot turn the device where your probe is sitting on too much, because then the rays cannot get through. And this causes the fact that, so for low dose, you have a sinogram where you maybe only have every third column. But now you have a sinogram where you have a whole chunk of missing data, which is much more difficult than low dose. So this is clear. I mean, if you have a whole chunk of missing data, it's usually certainly much more difficult to reconstruct from that as if you have, let's say, every second, because then you can interpolate it. Okay, so let's be a bit more precise if you're interested in that. I mean, one can, again, phrase this all mathematically. The CT scanner samples the radon transform. You can write down exactly how this looks like. It's in integral over lines at different angles, at different offsets. And you can also phrase the fact that you have a limited angle, again, very precisely mathematical. Okay, so what is the problem now? The problem is that if you now solve with these traditional solvers, and let's say you have a 60-degree missing angle, that then, so this is a very classical reconstruction from CT, so-called filter black projection. And this is what I showed you, sparse regularization with shieldeds. And so you see it's certainly better, but I mean, it is not a suitable reconstruction. So just compare these images. You see here missing parts. Here everything is very blurry and so on. So this is something which is not acceptable. And so this is now a point where these methods reach their boundary, because such data is too complex for modeling it precisely with mathematical tools. And so their learning now becomes extremely effective. So then, I mean, deep neural networks enter the stage. Okay, so now basically, I mean, in a nutshell, we have here still our measurements, but here now for the reconstruction part, we use also neural networks. And we will see different ways how to do that. As said, because natural images are too complex for mathematical modeling. And typically, I mean, also we need some a priori knowledge about the reconstructed solutions. Okay, so yeah. So this was maybe the first approach which was used. We have here our sinogram. We recover with a classical method, and then we use a neural network for improving it. Because neural networks are really good for denoising, and so therefore we have these two stages. So it's a very ad hoc approach, but it worked quite well. So the neural network learns, basically, if you train it this way, it learns the structured noise, because this noise which appears here and comes from the reconstruction is certainly different from Gaussian noise. So it learns how to deal with the structured noise. And in that sense, it's also a little bit coupled to the physics of the problem. So this approach where you still use the physics of the problem, because here you have your classical reconstruction, and then you use the neural network to its advantage. So this is maybe the first hybrid model, or the hybrid reconstruction strategy. Hybrid meaning combining classical approaches with here deep neural networks. There are various now approaches one can take, and one can classify them typically in three different approaches, three different classes. I might say one are more supervised approaches. So the first and the easiest, the easiest maybe because you don't need to think much, you just put everything in your neural network. You train a neural network end to end. So this is, you have your data, but the problem with this is, first of all, typically you don't have that much data, in particular in the medical sector. And so therefore, if you have additional knowledge, like the physics of the problem, it would be a waste and also a huge problem if you just train your network end to end on this limited amount of data. Also, training it end to end, if it's a very complicated situation, it can become more unstable because the network basically needs to do all the heavy lifting of learning all, let's say, everything about the scanner, which is actually not necessary because we already know it before from, let's say, physics. So in that sense, I mean, my suggestion would be always to not do something end to end, but to be a bit more, let's say, smart and incorporate knowledge into the algorithm and the network. So that is the second point, incorporate information about this operator K in the neural network. Combine it with classical approaches. On the previous slide, we saw maybe the easiest one, first the classical approach, then the neural network. There are also approaches where you have, let's say, your classical algorithm, you break it open because it has also certain parts like a denoising part, and in the algorithm, you replace then certain parts with a neural network and so on. So this is plug and play. So these are basically, I might say, supervised. Then there are what I call semi-supervised. So this is typically you have your solver, which we saw before, and now you replace just the regularization term by a neural network. So the neural network doesn't really work on the complete data. You just train it to serve as a regularizer. And so there is what's called a zero regularizer and so on. So this is maybe a second direction, and then a third direction, what I might call unsupervised approaches, where you basically take a neural network in a certain sense as a prior per se, without any training, and surprisingly, it works also quite well. There's this very famous article about deep image priors. Okay, so I would like to show you now a little bit more in detail about supervised approaches. Before I do that, let me also say concerning neural networks, here there's a very classical architecture which people typically always use. And these are units. For some reason, they're extremely good for inverse problems. And then it's mainly a question of how many layers to take and how and so on. So how does it work? Here you have your input image. So you work here through the layers. The size is compressed. And then you enlarge it again to the output, and then you get your output image. Now, during this compression stage, the hope is that, I mean, the key features which you need for your reconstruction are extracted.
Gitta?
But yes.
Is it okay if I ask a couple of questions from Slack?
Yeah, sure, please.
Sure. One question is from Kate. Can you explain the structured non-Gaussian noise more? How is the domain knowledge built into the neural network? The two questions.
Oh, okay. So I presume that that question tackled this here. So what I meant here was, this is, so what the neural network, the task the neural network has to solve here is not classical denoising. Because here you have noise, but now you reconstruct. Basically, so here it could be Gaussian noise, but now you view this through the filter of the reconstruction. So the Gaussian noise is turned to some other type of noise, which has now some structure also depending on the data. So the neural network doesn't find here this classical Gaussian noise, but it finds here some noise which now comes through this procedure, through this inverse procedure. And so the network now, if you train it this way, so what do you do to train this neural network? Well, you take here sinograms, maybe you put Gaussian noise in it, and you take here natural images, the canonical images which fit to that. So basically you start with images of this type, you compute the sinogram, and that way you get these pairs which are now correct. And so basically you now train the neural network to deal with that kind of noise. So that's what I meant with structured noise. The network here would not be a classical out of the tool network which deals with Gaussian noise, but you have to, maybe you can start with one, but then it would be good to retrain it or to fine tune it on this type of noise.
I think the next question is also related from Dieter. And the question is about, I'm wondering how they had ground truth or less noisy image here when training the neural net. Was the sinogram artificially noised?
Oh, I see. So here, yeah, so I have to think how they, so what I presume, I mean, what they did is so here, I guess yeah, so you take images, I mean, typically you train your neural network first on artificial data, and then you train it on real data. So here you could take, let's say, images, you compute with some noise, you compute the radon transform. Then you would use this inversion process. Then you would take what you get there and train the neural network from this to recover the clean image. So that way, I mean, initially here you put Gaussian noise, you compute radon transform, invert, and then you train the neural network to deal with that type of noise. Okay, so yeah. Sure. Okay, so yeah, so this is typically this unit architecture, and as said, since we compress here and lose information, the unit also has so-called skip connections from, let's say, this layer to this layer, from this layer to this layer, so that some information can be also brought to the other side without some degradation. Now, so if you have an inverse problem, the unit is what you want to take. Okay, so let's look at a general strategy. So as said, I mean, these model-based methods are very reliable. So we know exactly how they work. We have error bounds for those. So the first step should be, I mean, from my perspective, usually to use model-based methods as far as possible, as far as they're reliable. And then augment with AI-based approaches like deep neural network only where it's necessary. So to use them in a surgical manner and exactly how they are needed and where they are needed. So for instance, if you have missing data, I mean, not train the network end to end using the classical method and then using the neural network where it's needed, but finding out where it's needed is often not that easy. So let me show you some examples. Yeah, and so then combining both worlds. Now, another guiding principle, which I mean, from our perspective is usually very effective, and what we also pursue in my group is, as said, I mean, edges are key features of images. I mean, they make images sharp, they show the important structures. And so in that sense, representation systems which deal with precisely edges like shielded transform is very effective. So you can phrase this mathematically very fancy. So what is usually necessary to consider are not just the edges, but also the direction in which the edges occur. And so there's a fancy term of a wavefront set. So a wavefront set of an image are the edge points together with their direction. And so if you have complete knowledge on that, I mean, you get already very good reconstruction. So these are the principles we typically employ in my group. And so advantages, then you have the theoretical guarantees from model-based methods. You get reliability because you only use the neural network where you cannot get the result otherwise, where you don't have any other choice in a certain sense. Also, the neural network typically has a much better output because it doesn't need to do that much heavy lifting. It can get the same performance with much less data because it doesn't need to solve such a huge task as if you would train it end to end. Yeah, and it's also less than a black box. So let me now apply it to limited angle computed tomography, which has the problem that if you have a missing angle, and let's assume this angle here is missing. Sorry, this angle is missing. Yeah, so if this angle is missing, you see, you just scan in these directions. That means these edges will be always smeared out. You can detect these edges very clearly, but these edges not, because for detecting these edges, you also need to scan in this direction. Yeah, so some of these edge structures are very visible and others are not, depending on where your angle is and what you are missing. So basically, you can phrase it very fancy, since depending on the direction of the edges, they are visible and others are not, that what you want is to in-paint this wavefront set. Yeah, and so here is the workflow. We will see the algorithm in a moment. So first, what we did was we solved it with sparse regularization using shillets. This is the classical method. The results it gets is not great, but now we can augment with neural networks to recover the missing components in a sophisticated manner and then combine both worlds. So let's look at how one can do that. Yeah, so this is the classical reconstruction sparse regularization. You see here the data fidelity term, which we discussed before, the radon transform. This is now your operator. The measurements G. Here you see the L1 norm, and this is now the shielded coefficients. The weight comes in because it's a multi-scale system and you need to weight the different scales differently. Then you get this not that great reconstruction. So now what we do is we do another shielded transform and look. So that will reveal some of these entries will be 0 in areas and others will be reliable and perfect. And that depends a bit on the angle. Because now you compute again the inner product of shieldeds with your image, which you get, this F star. And some will fall into this range where you didn't get any data. So these are 0 and others are reliable and perfect. And these we don't touch. We only now revealed which coefficients were not correctly recovered and only those we train. So these invisible ones, we now use a network and train a network to, from the visible ones, reconstruct the invisible ones. And then we put both together, what we get here from the network, plus those which are reliable, and then we bring it back into the image domain. So basically, we go now into the shielded space, into the shielded domain. There we see what has been recovered and what not. Use the neural network there, and then recover. Okay, and so what you get then is the following. So this is a 60-degree missing angle. This is the original image. This is a classical filter back projection reconstruction, which looks just awful. This is a relative error. This is a quality measure, which is very much dependent also on the visual, on the human visual system. And I will say a few words about this. Okay, so this filter back projection. This is another very classical reconstruction TV, which already looks a bit better. This is a sparse regularization with shieldeds. You see here, I mean, again, all the problems which occur. Now, the next is a neural network end-to-end, which is also not that great because there wasn't, it's usually the problem also that there is not enough data available. But now if you combine both, you see you get significantly better reconstructions. So in that sense, I mean, taking the best of both worlds is something which, from my viewpoint, is very effective. And if you like numbers, here are the numbers, the relative error, the PSNR, the self-similarity index, and this HARP psi, which is actually a measure we developed, and it is better than the self-similarity index with respect to human opinion scores, and it's also very efficient to run. So we also have a web page where you can go and test it yourself. In any case, in any of these metrics, you see the reconstruction with this learning the invisible is by far the best. Similar strategy a bit is also applied here. So this is a very classical problem where you want to detect edges and their direction for whatever application you can imagine. And again, here first a shielded transform is used and then a neural network to make it a bit more, let's say, detailed. Yeah, but so this is also, I think, one advantage which we saw is we go to another domain like the shielded transform, the shielded domain, and train a neural network there. It is much more effective because you prepare the data in a very good way for the neural network, and it already can see that, say, the necessary structures much more clearly. So this pre-processing for a neural network, bringing it in a different domain, is usually also something which has a huge advantage. Okay, and maybe as one last, there are also more sophisticated methods than what I showed you. So for instance, what you can also do is you can employ that you have a certain connection between the sinogram and your reconstruction image or the original image. And so another algorithm which we also designed was to first map the sinogram to the image back by a certain deep learning type algorithm, but at the same time look at the sinogram and extract the edges and their direction, bring just them back to the image domain, and use this then as a prior and do base both simultaneously. So you see this here. You have your sinogram. This is your, well, I mean, there's learned primal dual algorithm, which is another type of machine learning algorithm for reconstruction. But in parallel, you can extract this wavefront set. So meaning the edges to their direction. You bring it back into the image domain. Since this is a limited angle situation, you now have to in-paint it. And then you combine both the not that great reconstruction with this prior and get a very good, significantly improved reconstruction. So you can build, in that sense, very sophisticated algorithm by playing around with all those parts. And so here again, you see some images. This is the original image. Now we have a 40-degree missing angle. Filter back projection. Again, TV. Sparse regularization with shear lids. Look, also very bad. This is the learning the invisible, what I showed you before. Now, so PSNR 26, also not that great. Just this learned primal dual approach, just the neural network per se is worse. What we also observed before, so it's better to take the best out of both worlds. But now, if you go to these, what we call deep micro-local reconstruction, you get a significantly improved reconstruction. So putting a lot of mathematics in there, so looking at these edge structures, the wavefront set, using them as a prior, you get significant improvements. Okay, so I would now like to, in the last few minutes, to also then leave some time for questions and discussions, talk a bit about explainability and also a bit about limitations. So this is, let's say, the final part. So explainability, I mean, is, I think, an extremely important area. So we have a trained neural network. We don't know how it was trained. We want to know how it operates. We want to open the black box, basically. I mean, why are we interested in that? Where we could get new insights about which key features are important for a decision, because neural networks are really good in this, let's say, data mining. And that way, also from a scientific viewpoint, you might get some additional insights. But on the other hand, we also want to have information about how reliable the result is and check it. And so for the vision for the future is to get an explanation for any question a human can ask and also hopefully discuss with AI as you do with a human. So the both basic algorithms do the following. So let's say we have a 3. We have a neural network which says this is a 3. And then you want to know how relevant are the pixels in this image. And so typically these algorithms output a heat map, which indicates at each point how relevant the pixel was for the decision. And so here these red pixels were deemed now extremely important. So the network looked at those, and that makes a lot of sense because, I mean, these openings here distinguish a 3 from an 8. So it makes a lot of sense that the network takes care of that. So here the network did something reasonable. But one can also then ask, I mean, from, let's say, my viewpoint, what is relevance? I mean, what does it mean that this is red or this is maybe not that red? What are good relevance maps? Also, can we get higher level explanations? Because typically not every pixel is relevant, but maybe combinations of pixels. So we want to question an AI as a human about the reason for a decision. But I mean, something which is also neglected often is the explainability approach needs to be itself reliable. So if we rely on the explainability approach to tell us how reliable the AI was, but the explainability approach is, I don't know, unstable, then we cannot say anything. So the explainability approach needs to be itself based on theory. And let me also mention, I mean, since there's ChatGPT, it gave a huge push to this area because now, I mean, people are also doing research in using ChatGPT to communicate with AI. Very exciting times. Okay, so let me show you one approach, I mean, which we developed. I mean, it's comes from information theory, and it has the following viewpoint. So let's say, so information theory always deals with the question: someone has a message, Alice, she sends the message to Bob, but not the complete message, and Bob needs to decode. And so Alice sends certain things at a rate, so very few parts.
Excuse me, Gitta.
And yes, please.
Sorry, is it okay if I ask a couple of questions from
Yeah,
Slack?
sure.
Yeah.
Sure.
So there is one that is talking about different types of technique like dance for pre-processing images for neural network. And there are cases where pre-processing like brightening the image, increasing the contrast actually leads to worsening of the results. Are you aware of any sort of a study that compares different pre-processing methods when they're helpful?
So, I mean, in a sense, I mean, it's also a question, I mean, how you improve the contrast. Yeah. So here, I mean, it's in a certain sense done in a very natural way because, I mean, these shillets basically put a lot of emphasis on the edges, but not neglect any other parts. Yeah. So you still have, I mean, you can tune it in such a way that you get still, I mean, the complete image. You don't neglect anything. Other algorithms for, let's say, enhancing the contrast might degrade other parts of the images, yeah? And that then becomes a problem.
And the other question asks, can you please say how do you approach image reconstruction from the point of view of trustworthiness, specifically in medical domain, where introduction of AI in the reconstructed image can have catastrophic consequences? Is it important to maintain the structures of original degraded image, but also improve the overall quality?
Yeah, also an excellent question. I mean, so what I showed you before, these hybrid approaches, I think from my viewpoint are also a very good way to get more trustworthiness. I wouldn't say they are overall trustworthy, but you see the philosophy there is you use the model-based approach, which is reliable as far as it goes. And then when it cannot go any further and you don't have any other choice, then you use a neural network. And then what you could do is, for instance, check, for instance, with explainability approaches, whether something reasonable was done. So in that sense, I think this is the most reliable you can get so far. Certainly what we aim for is to have also then for the neural network part, a theory which tells you exactly, which gives you error bounds and so on to get true reliability. But that's still a bit away ahead. Okay. Okay, so now, I mean, the philosophy here of this approach is we have our original image. We want to check which parts are relevant. And so we have the original image, we have the neural network. We take out a certain part of it, then build a new image with it, maybe obfuscate with random noise to distort it, and then again check it, put it in the neural network. Yeah, and if this was the relevant part for the decision should not change too much. So this is a philosophy which is based on information theory, and you can also exactly then define the error which you make by just looking at the difference between these outputs. Yeah, so if this is the relevant part, then these outputs should be exactly the same. And so certainly you aim now for a concise explanation, very few pixels, but then, I mean, the error should be not too large. Yeah, so very few pixels and the error should be not too large. So that would be ideal. This you cannot solve, unfortunately, but this is then, I mean, a variant which is solvable. And again, you see it's in the framework of sparse regularization. Again, we have here our error term. We have here the sparsity. We want that the relevant scores are sparse. And we can solve this minimization problem. So let me show you some. Yeah, and that's also an advantage because this now allows mathematical performance analysis. Yeah, so here you see some images. So you have an image of a dog. The network says this is a dog. And you see here different explanations, and you see ours is tuned for sparsity. You get very concise explanations, and you see very clearly what the network looked at to detect that this is a dog. And so looking at the head makes also a lot of sense. Now, I mean, there are two generalizations which one can think of. One is masking everything with random pixels, looks a bit strange. So one can use an in-painting gun to extract a part of an image and then obfuscate it so that it's a bit more natural looking image. The second is, as said, we typically don't want to have pixel-based explanations, but maybe explanations which is a cluster of pixels. And so what you can now do, we just also talked about wavelets, you can do a wavelet decomposition of an image and then put the relevant to the wavelet coefficients. Okay, so let me compare this philosophy to image compression. So image compression, we also discussed it before. We have the input image, we compute the wavelet transform. Unfortunately, it's too small to really see it, but let me walk you through it. So we compute the wavelet transform, we select the largest entries, so the white ones, we replace the others with 0, we reconstruct, and then we hope that these images are very close. So that's classical compression. So you compress, you put everything to 0 in the wavelet domain, and then you hope when you reconstruct it, you still didn't degrade the image too much. Now here, this explainability viewpoint, which is in this philosophy, is similar. We compute the wavelet decomposition. We select the largest entries. Now we replace the others with random noise, or maybe with this in-painting gun, and then we reconstruct. And now we don't hope that these images are close, but we view them through the lens of a neural network. And then we hope that those are close, because that tells us how relevant, let's say, those entries were. So in that sense, I mean, this algorithm is very much in the philosophy of image compression. Let me just show you 2 examples in the end. Unfortunately, both not from health, but I mean, I hope you still get something out of those. So here, what you see is, as I said, understanding seemingly wrong decisions. So the network can do something wrong, and then you want to understand, did it do something really wrong? So now here, this comes from telecommunication, where we also work in. You see a city map, you see the red dots are cell phone users. You see here the white blob, which is a cell tower, and the network computes this black and white background, which indicates at each point how strong the signal is. Yeah? So for instance, if you stand here, you have a really bad reception because you have a lot of buildings between the cell tower and you. But now you see here is an area which is also black, which doesn't make any sense, because if you stand here, you stand right in front of the cell tower. So you can ask, did the network do something wrong? And the explanation which we then got from this algorithm was, well, the network based its decision to put this black area here on those structures. And in fact, those cell phone users have bad reception. And what turned out later on was there was actually a building missing in the city map. So the data was faulty. The neural network did something correct. So that way you can check whether something which might seem wrong is in fact maybe correct, but only there was a problem with the data. You can also check wrong decisions. So here the network decided that this is a diaper, although it's obviously a man with a dog, and that this is a screw, although it's obviously a man with a sweater. And now I will overlay this with the explanation, and you will see what the network has seen to reach that wrong conclusion. So I will put it on top. And what you see is this looks a bit like a baby. So a diaper is not that far off. And this looks here a bit like a screw. So therefore, you can unravel what the network has seen to reach that wrong decision and can cope with that and can correct for that. So therefore, explainability, I think, is an extremely important area. And research is also now pushed there in different directions. And I think for the future, and in particular also in the medical sector, it will be absolutely necessary to also use those tools. Also relating to the previous questions which we have, I mean, this then also gives you more reliability. For instance, if you detect cancer and you ask how the network has detected this skin cancer, and then you see maybe, well, I mean, it looked at structures where there was just a hair in this part. And so then you can correct the decision and maybe say, well, I mean, there was just this hair, so it looked strange, but this is not cancer. Okay, and then the last very few minutes, let me just finish with a word of caution of limitations, because I said, I mean, AI is not a Swiss Army knife, so there are limitations. And what one can think of and what we explored is, you see, you train everything on digital hardware. So you have typically continuous problems. I mean, in real world, most problems are of continuous nature. But then you break everything down to zeros and ones. And you can ask, does this cause any problems? In particular for AI and for reliability. Yeah, and so one can ask, there's this beautiful theory of computability in computer science. So computable problems are problems for which the input-output relation can be computed on a digital machine for any accuracy, which is what we want. If you want reliability, we don't want that we always make a consistent error. So that would be a huge problem. So if something is non-computable, well, I mean, you can certainly still solve this problem, but you don't have any guarantees for success, for correctness. In particular, even if you're in a theoretical analysis, if things are not computable, I mean, everything is you cannot even check whether you stay within this error bounds. And as said, a digital machine, there's a very canonical model for it, which you might have heard of, the Turing machine, which is the model for any digital machine, like GPU, CPU, and so on. Okay, so I mean, what one could find out is that in fact, I mean, many problems, like certain finite dimensional inverse problems, are not computable on a neural network. Yeah, so this is very disappointing. In particular, since these are also not, let's say, too ill-posed problems. I mean, there are also problems which are of a very natural type, which are then not computable, in particular, since computations are almost exclusively performed on digital hardware. Yeah, so there's this inherent automatic unreliability, which says, well, I mean, no algorithms exist, which, I mean, for those problems, which on digital hardware derives neural networks which approximate that to any given accuracy. The output is then not reliable, and also it could point towards why we see these instabilities and non-robustness. And let me say, this is not a problem of the problem you want to solve, it's a problem of the hardware, yeah? Because we train everything on digital hardware right now. Okay, so this is very disappointing and it's a bit unsettling. But then on the other hand, there's also a way out, which is to go to analog machines, because then suddenly things become computable. So it could be, and this is what I meant right at the beginning, it could be that we need to rethink where we train our neural network on to get true reliability. Maybe we need to rethink the hardware itself. And there are actually very exciting future developments, like, for instance, neuromorphic computing. There are neuromorphic chips already, which mimic the human brain much better and which are actually analog chips. There's biocomputing, very exciting. You aim to compute in the cell. And also quantum computing, not the qubit quantum computing, but the true quantum computing, which uses photonics. All of those are analog hardware. And so the question is, do we need to augment, for instance, digital hardware by analog hardware? And so, I mean, there are a lot of problems which are not computable. Let me not go too much into details, also some classification problems and so on. A lot of problems, unfortunately, which are solved these days, but with this caveat. So the vision would be then, I mean, getting truly reliable AI for many problems, it might need to rethink the hardware and go to the analog world. Okay, so let me finish with some conclusions. Although AI is very impressive, we still have major problems with reliability. I showed you a bit that classical solvers reached their limit. We discussed classical solvers, saw an introduction on that. We saw what is basically, I mean, some directions you can do, you can go for concerning hybrid approaches. We discussed a little bit explainability and also limitations with digital hardware. Now, before I finish, let me also say, since we are talking about reliability, so let me just finish with one small ad. I hope it's It's allowed because we just started the Konrad Zuse School of Excellence in Reliable AI in actually Munich, which is set up between both universities, the TU Munich and the LMU. And what you see here concerning areas, there's also medicine and healthcare, which is one of 4 research directions, and also algorithmic foundations, everything intertwined with reliability. And so the idea, this education program is for the master level, and also for the PhD level. And so with this, I'd like to conclude, and thanks a lot for your attention.
Thank you very much, Gitta.
These theorems about uncomputability sound very strong and a bit scary. Could you give a core idea of the theorems? What is it that doesn't give the digital computers the possibility to solve these problems?
Yeah, so first of all, I shouldn't say, I mean, not every problem is not computable, but I mean, so these are results which show that there are problems which are not computable. And in fact, I mean, one could imagine it has to do with a condition number, but there are also problems which have a good condition number for which it's not computable. We could also show that, I mean, there are certain problems which have, let's say, a consistent error, which you cannot, let's say, go below. I mean, the key problem is that most problems are of a continuous nature. So think, for instance, I know, solving partial differential equations and so on. I mean, the whole world is continuous, but then, I mean, you break it to zeros and ones, and so you also cut it in a certain sense because you only have a finite, let's say, memory where you need to store things. So this causes these problems. So in the analog world, there you have the huge advantage. So for instance, these neuromorphic chips, they are based on so-called spiking neural networks. So spiking neural networks, the normal neural network sends, let's say, bits to the next layer, but a spiking neural network sends potentials to the next layer. And so this is this continuous nature. And so there you can capture much better, let's say, the continuous phenomena which your original problem has. So this is basically the the underlying obstacle which digital hardware has to face and which it cannot cope with because it has only, let's say, this limited expressivity in a certain sense.
This is somewhat of a follow-up question. For me, I'm having trouble distinguishing between explainability and uncertainty, given what you were. So I can understand the uncertainty when you have to quantize things, but perhaps not the explainability of having this quantization effect.
Yes, that's also a very good question. So, I mean, explainability, so what I showed you is typically if you have classification. Let's say you have an algorithm which says this is cancer, or this is not cancer, or this is a certain type of cancer. And so for classical inverse problems, you would, if you don't have a classification decision afterwards, for the classical inverse problems, you would typically more aim for computing an uncertainty map on your recovered image to show which regions are how certain. But so, I mean, the algorithms which are available today are, from my viewpoint, I mean, not satisfactory in that sense. I mean, they're very limited because also it's still very difficult to unravel how certain a network is about something. So there are these Bayesian neural networks, for instance, which have a bit of an advantage in this respect. But I think there's still a huge gap. But this is uncertainty versus, let's say, these explainability maps.
Thanks very much, Professor.
Great. Thank you very much. And thank you, everyone, for the great questions. And thank you very much, Professor Gitta, for the great talk. So with that, we go for the coffee break and the photo, and then we'll come back in 30 minutes. Thank you.